Good afternoon, everybody. During 7th lecture, I will talk about general properties of spectrally inhomogeneous media. No matter how perfect synthesis method we use, every real ensemble of nanocrystals dispersed in some environment will possess unavoidable inhomogeneities. For majority of matrices, this is first of all size distribution. But even if we minimize the size distribution, the crystals remain to differ in shape, like here, in impurity and defect concentration, in local environment and even charge. All these factors lead to the inhomogeneous broadening of the absorption and luminescence spectra of the system. That is why spectrally selective techniques are usually used to investigate the properties of the unhomogeneous medias. Real systems consisting of particles with discrete energy levels exhibit absorption saturation under intense optical excitation. In case of the two-level particles, a system of steady-state rate equations can be written, where n is the total number of particles, and 1 and n2 are the population of the ground and excited state respectively. A and B are the Einstein coefficients for spontaneous and stimulated transitions. When we have very intense optical excitation, its radiation density is really very high, as well as the Einstein coefficient for stimulated transitions, B. Here we have this expression a lot more than the Einstein coefficient, A. It means that in this case, we have the population and the probability of the existing electrons on both the ground state and excited state equal. Here we have that the half of the electrons associated on the ground state and the half of the electrons associated on the excited state. In this case, the absorption saturation is maximal, then absorption coefficient is equal to 0, and the relation between absorption coefficient and radiation density has this form. This relationship implies negligible radiationless transitions and transitions stimulated by equilibrium radiation. It is valid for every system with discrete energy levels when the rate equations are linear. Here n is the non-linearity parameter. In case of the multi-level system, the non-linearity parameter of a given transition is determined by the probabilities relevant to other transitions. It means that saturation of one absorption channel is determined by the properties of the entire system. What is absorption saturation? When we are talking about linear absorption, we have a two-level system where all electrons associated on the ground state. Then a photon falls down on the system. If the energy of the photon is equal or more than the energy gap of these two energy levels, then the absorption happens. It means that electron goes from the ground state to the excited state. And he is here now. But when we, and after some time, it will relaxate radiationless on the ground state again. But if we are increasing the intensity of the optical excitation, it means that several electrons can go, or are forced to go from the ground state to the excited state. You know, it's the stimulated transition. But if we increase more and more the intensity of the optical excitation, it means that more and more electrons will have to go from the ground state to the excited state. Until we got this situation, then all electrons associated on the excited state, and then another photon falls down on this system. It can be absorbed because none of the electrons can absorb it because they have already absorbed another photons. And at this situation, saturation is maximum and the absorption coefficient of the system will be equal to 0. But in experiments, the light intensity is usually expressed in watts per square centimeters rather than in radiation density. That's why we can rewrite the expression from the previous slide in this form, where this is the saturation intensity, which is dependent on the lifetime of the level and the resonant frequency. In case of biomolecular kinetics, the rates of all transitions obey quadratic dependence, and the rate equation here will have this form, which was found to be valid for a two-level system also. Let's compare the intensity dependence of absorption coefficient for monomolecular and biomolecular recombination. When an ensemble of particles in a monomolecular recombination system is irradiated by isotropic light, we obtain a solid line. When the same ensemble of particles is irradiated by a linear polarized light, we obtain the dashed line. Bimolecular recombination in the 2, 3, and 4 level system has a more complicated form. Into 2-level system, curve 1, the absorption function corresponds to this equation. But in the 3 and 4 level system, simultaneous population and depopulation of the excited state and intermediate trap state, this one, results in more complicated saturation dynamics. In 4-level system, the initial part also corresponds to this equation. Then a pronounced step happened due to redistribution of the recombination between competitive paths, this path and this path. The final stage in all cases, here and here, obeys the dependence that is similar to this one. 3 and 4 level systems with bimolecular recombination are relevant to impurity semiconductors with 1 or 2 trap levels. This system possesses more complicated saturation dynamics because of the intensity-dependent recombination rate and redistribution of recombination channels between competitive trap states, this state and this state. The spectral shape of an elementary absorption band is determined by dephasing dynamics. In the case of the constant dephasing time, the shape of the absorption band obeys a Lorentzian law, this equation and this shape. In large number of cases, population of the excited state doesn't affect the dephasing rate. Absorption spectrum of the system consisting of identical particles with constant lifetime under optical excitation obeys a Lorentzian with intensity-dependent amplitude and line width. Here we can see that with the increasing of the population of the exciting state, the intensity of the Lorentzian band decreases, while the width of the band, which is usually calculated at the level of the half of the maximum, increases. This consideration implies identical absorption line shapes inherent in every particle, and this is called absorption spectrum inhomogeneously broadening. But in real systems, the broadening is inhomogeneous. Examples of nanocrystals possess inhomogeneous broadening because of the size and shape distribution, as I was talking about previously, local environment fluctuations, and chemical inhomogeneities. Here we can see inhomogeneous broadening in case of equal waves of all subbands. But under this condition, the steady-state excitation by spectrally narrow radiation is usually used. So we use very spectrally narrow excitation. It means that only that particles that are resonant to the exciting radiation will possess absorption saturation. This is called selective absorption saturation. But also we have power broadening, which results in the increase of the width of the whole burned spectrum with the increase of the pump intensity. Power broadening results from the increasing contribution of particles whose absorption wings overlap the excitation frequency. Here, the bandwidth of the hole of the burnt hole will be expressed by this equation. The absorption coefficient in the center of the hole burning in the spectrum falls with intensity according to this law. And here you can see the inhomogeneous broadening in case of the Gaussian distribution of some bands. With narrow band excitation, selective absorption saturation results in a dip, with growing depth and width, and successfully growing intensity of optical excitation. But some properties of the systems cannot be measured via absorption spectrum, so we have also investigated the luminescence spectrum of the system. But you should still remember that it will be also inhomogeneously broadened. That's why we usually use the method that is called fluorescence line narrowing. Here we do not need to have a very powerful laser source with very high intensity as in previously spectral hole burning method, but also only a lamp with wide spectrum and a monochromatometer. Usually we obtain such elementary absorption and emission spectra, but when absorption and emission spectra are very broad, like in this example, tunable excitation at the low frequency wing of the absorption band results in very narrow emission spectra, which is correlating with excitation wavelength. From this, we can estimate the first excited state energy as well as the individual Stokes shift. Excitation spectra provides us information about individual absorption spectrum, including high excitation states. Basically, excitation spectrum correlates with the absorption spectrum, but two aspects should be mentioned here. First of all, some of the excited state pronounced in the absorption spectrum may not be efficient in luminescence excitation. This is one of the reasons why excitation spectra is determined not only by the wavelength-dependent absorption, but also by wavelength-dependent quantum yield. And the second aspect is that luminescence intensity, in case of the negligible reabsorption effect, is proportional to the number of the absorbed quanta. This means that it is proportional to the absorption intensity. Therefore, an evaluation of absorption features via excitation spectrum is meaningful as long as the extent of the exponent is less than unity. Then it is a lot more than unity. It means that luminescence saturates and it doesn't depend on the excitation wavelength. A distribution of resonant absorption and emission frequencies may occur along with the distribution of decay time. Here, the most appropriate method to use is a time-resolved spectroscopy. If no energy transfer occurs between different particles within one ensemble, then distribution of decay time results in monotonic shift of the emission maximum with time, with no overlap of the time-resolved spectra. But if such a transfer takes place, it results in the burn-up of luminescence at one side and its simultaneous quenching on the opposite side, here. Discussion so far has been related to the evaluation of the individual spectral features in spectrally inhomogeneous media by means of the spectrally selective techniques. But along with spectrally selective performance, laser sources allow us a spatial selection of molecules, ions, or nanocrystals. Single-mode laser radiation with Gaussian beam cross-section can be focused to a spot of this diameter. It means that using high-quality microscope objectives with f-d ratio almost equal to 1, we can obtain for wavelength of 500 nanometers, so the center of the optical spectrum, a focal spot of the about 1 micrometer in diameter. In case of rather dilute solution, this corresponds to a few molecules inside of the excitation spot. Here you can see possible versions of single molecule excitation. In first case, the same objective, this one, is used for excitation, focusing, and collection of emitted light by the means of a semi-transparent or beam-splitting mirror. This light is collected by spectrometer with the cooled detector and big data acquisition period. In the second case, tapered optical fiber provides near-field excitation of the single molecule, whereas emitted light is collected through transparent substrate. In this case, combination of the solid transparent matrix and photolithography are successfully used. And in third case, a wide laser beam is used for excitation, whereas the special selection of the molecules is performed by using a thin metal film with small holes of the diameter of about 1 micrometer, and the excitation of the molecules or nanocrystals is obtained via these small holes, which can be obtained, for example, by chemical etching. Thank you for your attention. Goodbye.